In this work, body shape of soft robots is synthesized without prior knowledge of the legs and arms. The only requirement is the desired locomotion task, starting with a simple initial shape, a cube embedded with a pneumatic actuator. Through gradient-based topology optimization and 3D printing of soft materials, we create soft robots that function in the real world. To achieve this, we constructed a differentiable multiphysics simulator. The simulation of locomotive soft robots involves large deformations, hyperelasticity, fluid structure interactions, contacts, and material viscosity. To handle these complexities, we utilized the material point method. The soft robot is discretized to particles. The exterior forms the design domain, while the interior contains air chambers, with the air modeled as a fluid. In topology optimization, the object shape is represented using fictitious density. We optimize the density distribution to maximize the travel distance L. The first step is forward simulation, which evaluates the actual travel distance. For optimization, the gradient of the travel distance with respect to the density is required. To compute this, we perform backward simulation. Here, we use automatic differentiation techniques to trace the relationships between variables backward. And then, we update the density field. By repeating this process of forward simulation, backward simulation, and updating the density field, we synthesize the optimized shape. Now, let's move on to the results. First, we will discuss Result 1, Walker. The walker is optimized for the task of locomoting horizontally on a flat ground. From a simple cube, structures resembling front and back legs emerged. The locomotion performance improves as the optimization iterations progress. In the optimized result, the walker efficiently moves forward by kicking off with its back leg. For fabrication, surface data is extracted from the particle density data and 3D printed using digital light processing. Here is the experimental result of the walker. We can see that continuous locomotion is achieved in the experiments. We can see that the locomotion in the experiments closely matches the behavior observed in the simulations. Furthermore, the walker demonstrates robustness in environments not originally considered, such as inclines. It can walk stably on inclines of 10% and 20%, only reaching its limit at 30%. Then what if we optimize the shape for the incline from the beginning? Here is the optimized result for a 30% incline. Unlike the flat ground case, the legs are divided into left and right and feature many thin structures. These characteristics provide stable traction on the incline. For a steeper incline, 30°, more complex shapes are obtained. The back leg adopts a more flexible shape. By lowering the front center of gravity, the walker prevents rolling backward. Now, let's move on to Result 2, Climber. This is a more challenging task of climbing vertically between two walls. As optimization progresses, complex structures emerge at the top. The optimized result features 4 arm-like structures at the top and 2 leg-like structures at the bottom. Comparing the optimization history, we can see that unnecessary material is removed, and the performance gradually improves. The complex linkage-like structures at the top are designed to pull back the hands, while extending upwards when the air chamber inflates. The optimized result was fabricated using the same 3D printer as the walker. In the experiment, despite variations in posture due to disturbances and errors, continuous vertical locomotion was achieved. Compared to the simulation, it is evident that the limb-like structures move in a similar sequence to achieve upward locomotion. Notably, this complex motion is accomplished using only a single channel actuator, achieved solely through optimization. Thank you for your attention.